Good morning, everybody. So thank you for the introduction. My name is Louis Moreau, and I'm coming from Canada. And I'm here because I was here 2 years ago. I was presenting on the same subject. At that time, I was describing what is haze, anisotropy, clarity, and interference. From 2017, I've been working in that field to try to figure out what happened with problems that we had. What happens when I'm in an Apple store and I look at these patterns? What is causing that? So that was my main question. Why do I have this blue line in this thing when I have a blue sky? Why do I have this freaking pattern in my glass on that Boston Apple store? So that's really what triggered my quest for answers. When I started, I had no clue of what was causing that. Now I know what is causing that, and I've worked to make it better. But I wanted to share this experience with you guys and in fact, with everybody. So at the last GPD 2017, we had a workshop on anisotropy, and we decided that a year from now, we're going to meet again outside GPD and discuss where we are in terms of progress in analyzing that and everything. And that meeting happened last year in June. It was hosted by Apple in Cupertino. I don't know if Adrian is here, but we had 31 people gathering from all over the world, some scientists from Germany. We had scanner manufacturer, we had glass manufacturer, and what I want to share with you is what we discussed in that meeting, which gives you an idea of where the world is on measuring anisotropy. My personal belief is for every phenomenon that you have to, if you want to make it better, if you want to improve it, you have to have an accurate measurement. So that's my personal belief, is that you have to have a numerical value that will give you this is good, this is better, this is less good, and that's what I've been working on. And that also lead me to, in that quest, after the Cupertino meeting, what I call, or the Cupertino Summit, we came up with a task group, and we are coming up with an ASTM standard on how to measure anisotropy in large pieces of glass. And that's what I'm going to present to you today. So it's a work in progress. There's still things to be done. But when I started to do this, I wanted to do something simple, something that people would understand, and we could use that as a building block for more development in that. So today we're going to be looking at definition. As the presenter before me gave presentation, I'll go rapidly through that. But we also will look at in our Cupertino meeting what was the stakeholder opinion. In fact, the main guy who made that presentation, Saverio, is just standing there on the back. I see him. And we're going to look also at what are the existing scanner technology, which one you can rely on. So we'll have 5 different manufacturers that makes that, and I'll make a nice summary table for you if you want to buy one. And then we'll briefly look at what is the ASTM task group, where do we stand right now at the moment with our standard. So, just rapidly, anisotropy, if you look at the word itself, it's the opposite of isotropy. Isotropy, I can tell you that water is isotropic. Air is isotropic. Vacuum is isotropic. Annealed glass is isotropic. It means that wherever direction you look at it, you have the same results. Vacuum, annealed glass. But wood is anisotropic. Wood is anisotropic because when you split wood, it's split easier in one direction. So the physical property of wood are different depending on the angle you attack it. So that's why we use anisotropy. It's because we have a different characteristic depending on the angle that you look at it. So that's the basic of the word itself. In fact, the word anisotropy, we apply it for glass, but the real word that we should be using is birefringence. This is the physical phenomenon that describes what happened when you look at those gray patterns on a facade. So the word birefringence, and that's when it becomes a little more complicated. So it's, and Reggio explained it a little bit. What happened is that you create, when you heat treat a glass, or when you cool a plastic in an interlayer, you actually create mechanical stress inside, and mechanical stress that are not the same everywhere. And what our eyes see is the difference in these stresses. And why it does that is just because you have mechanically the molecule are at different distance, and they change the speed of the light. They change the index of refraction. That's other terms that you will have to master. But that's what creates that, what we call so the birefringence phenomenon is that. So one ray is split in two pane, and all this happens only in when your incoming light is polarized. So you're going to recognize some of the figure that Reggio presented. So this one is from Saint-Gobain, and again I'm talking about our Cupertino summit. That's why I'm showing who presented that slide. But you have the same sketch that Reggio presented about incoming polarized light gets split in two directions, and the emergent light are separated by a small distance. We'll see that. That's, if you like the equation, that's the equation of it. Then, if I finished on birefringence, so it's basically an heterogeneity between different zones in the glass that result in, because of tempering, because of the way the air is distributed by the air jet and everything like that. Also, anisotropy exists in plastic. That's one thing that we have to understand. So when you laminate glass with a stiff plastic, like Century Glass, or like DG from Eastman, stiff PVB, you will get anisotropy because, but in a different manner, with more retardation. So again, we're looking at a different slide that we had in Cupertino. That one was from Eric Armstrong. It described pretty easily, I mean, it's very local, what happened in the glass and why we have those heterogeneity. I go fast on that. Finally, retardation. It's in the birefringent material, in the tempered glass, for example, or in a laminate with two tempered glass and a stiff interlayer. You will have differences in the speed of the light or the index of refraction, and those zones will show up to your eyes. And the measure that you have is this little part that we saw there. It's measured in nanometer, or what is the distance between the things. So the fundamental units that describes anisotropy is nanometer of retardation. Again, we see the same retardation between those two vectors. And depending how much retardation in nanometer, you will have different colors. So when we talk about tempered glass, you're looking at retardation between 30 and 120 nanometer in this region. That's why you see on the building it will look tints of gray and black. So that's what explains it. But when we deal with plastic, like when you look at Century Glass, and if you remember my first slide, you get something blue. So you're getting 600 nanometer of retardation. So different, same phenomenon, different expression. On top of that, Reggio also mentioned it, depending on how you look at it and on your environment, the glass will look differently. And Saint-Gobain, again, worked a lot on that, with Stéphane made a presentation in Cupertino, and noted that depending on your angle, you will see it on certain level. You will not see it on others. You will see it, it depends on the environment and the way you look at it. So, after that, Saverio came and tell us, so Saverio is a guy that works for Skanska in UK. So he owns a lot, Skanska built and owns buildings. So he's a real, he knows about anisotropy. He presented at GPD 2015. So he was really one of the first guys to talk about it, because he's annoyed with that. Because the industry has said, oh no, this is inherent to the glass processing and we cannot do anything about it. But so Saverio have done a thorough work on determining what are the standards available and everything. And he stuck with that. So people have been trying to avoid using heat-treated glass because of anisotropy. One of the reasons is that, because it's unpredictable and you don't know what happened. So there's no specification. The standard don't talk about it. There's no measurement method. So it's pretty vague. And everybody knows that if you heat treat, it cannot be anisotropy free. So you have to quantify it, get a number, get something, get a mapping of it. So that's the thing. We need to change something. And so that's what brought me and to push on it and to come up with an area where we can do something with starting with a building block in ASTM. So going forward, we'll have something objective to work with. What happened if we use nothing? I liked his slide. So increased number of undeliverable specifications. That's what he's confronted as an end user. That's his problem. Costly legal dispute and situation that get everybody's confused. And the glass quality does not improve. So, what happened since last year? So again, we're into presentation. So now I'm getting into what are the machines out there that will tell you what is the anisotropy level in a piece of flat glass. I'm going alphabetical order, Archon, but also Archon has a nice history because they're first with the A, but they're also the first that have developed a system. And they did that at the beginning with Glaston. I'll show you later on what machine they developed. But they were conscious about that. They're a German producer. And they were conscious about that, and they worked a lot about that. They have a guy that is super passionate about, Herman is super passionate about anisotropy. So he designed a machine, and he would make it work with Glaston and everything. However, the first machine they designed with Glaston was super slow and could not be used on the tempering line. So they departed each other, so there's no more work between Glaston and Archon. But Herman, who was working over there, was really passionate about it, so he decided to build another machine for himself. But it's quite complicated. When it comes to measuring anisotropy, it's not an easy task. It's not really easy. So he came up with Illis, which is another German company. But Illis has been involved into photoelasticity for 15 years. So they're quite thorough with that. And they joined together, and they created this first scanner that you see here. And their scanner works with pretty complex array of... what they produce is a polarimeter. So it's a machine that not only gives you the amplitude or the retardation value, but it also gives you in which direction the retardation is occurring. So their machine is pretty sophisticated. But Archon, being a glass producer, they have not delivered a lot of machines. I think they have a few machines on the market right now. But their machine is pretty sleek, and it gives nice results. So as a quick comparison, I start my chart. Archon, they use, as a light source, they use a LED source, and it's a polarimeter. So polarimeter gives you the amplitude of retardation in nanometer, but also in which direction, or which azimuth that polarization takes care. They use circular polarization, so if you move the glass around on your table, or if you don't align the glass correctly in the furnace, you will have the same result. The other thing is they use train cam cameras, so they don't rely on RGB correlation. So they make measurements with in a polarimeter environment. So this was the first machine that was designed by Glaston and Archon. So that was the antiquated machine, not antiquated, but it was a very, very precise machine. But the only problem, it took 2 hours to scan a normal piece of glass. So that was abandoned. This one is right now in a research institute in a research company in Germany. It was bought there. Now their new iLook system integrates into the tempering line as a scanner for the final thing. So this is the iLook. Their machine works also with LED panels, but they don't use a polarimeter. They use just an RGB conversion. So basically, they have camera looking at the polarized light, and they analyze the colors to transform the colors into retardation value. And it does not give you a value in terms of the direction of that. It's just a polariscope. So they use LED panel, polariscope, linear. Their capture are high resolution. Okay, their polarization on the machine is linear. So it means that if you change the direction of the glass on the tempering bed, you will have a different result. You saw that in radio presentation before, and that might not be the best way to do this. But at the same time, it's a good diagnostic tool for the furnace operator. Next one, alphabetically, is Light Sentry, a US company that has been into the distortion inspection business. So they have 230 installations all over the world, and they're used to plant environment. Their machine is thorough, precise. It gives a good reading of surface. And they wanted to expand into the anisotropy market. And they quickly also discovered that it was not easy. So what they did is that they went with Stress Photonic, which is the US pendant of Illis. So it's a company that has been on the market for 15, 20 years, making photoelastic measurements. So measuring anisotropy, but in different materials, and not always on scanners, but on punctual places. And they came up with gray field polariscope. So they also have, like Illis and Archon, they also provide with their machine a value of the amplitude and the direction. So that's a polarimeter. And if you look at that data can be used to predict what will be on the building, or what your glass will look visually. So Light Sentry, they use color balance light source, polarimeter. I don't know too much about their gray field polariscope, how they work. They won't tell you that. But also it's a coupling with distortion analyzing. Next in line is Soft Solution, an Austrian company that was associated with Fenatec, but now it's completely different. And they have their own US office, and they use their line scanner is a polariscope environment. And they analyze an RGB image, but they use multiple light source, different wavelengths, to give them a very wide range. And their machine allow allowed to, that has other function, like you can measure the defect, you can measure the edge stress, you can measure the whole position. I mean, it's a pretty complete scanner. So Soft Solution use multicolor. Their light source are telecentric. They don't use camera, they use a linear sensor, so it's a different technology. And they use circular polarization, so whatever you put the glass in, you'll always have the same values. And they can also give you blemishes, dimension, and edge stress. Last machine is Viprotron, a German company that is over here. They use single light source in the red, so they use red LEDs as a light source, polarized, and they analyze the RGB images. I go fast. So there they are, circular, high resolution. And one of the extra features of their machine is that they create the bottom. They also analyze the bottom haze. So if your glass is rolling it's dishing and rolling and scratching on the bottom, they will tell you that. So ASTM, where we are, we have done up to now, we had the kickoff meeting in Cupertino. Out of that group of 31 people, we're working about 12 people together. And we have, we try to have a monthly meeting, but up to now we had 8 meetings. And we still have 1 or 2 paragraphs to clear up. So our goal is simple, okay? I want to make it anisotropy for dummies. So I want just to do a test method. And we started with something simple, heat-treated monolithic glass. I'm not talking about assembly, I'm not talking about laminates, just heat-treated monolithic. That's our baseline. What we want is to educate people with this standard, all the people having a common terminology and people knowing what they do, what they establish a language for the industry, for the stakeholder, for everybody, for the architects, so people understand what's happening. And confirm the value in a numerical form. So that's our task. We don't want to set value, and certify that whether you're in Germany with this machine or in San Francisco with this machine, you'll have the same result. We'll have the same number. That's our goal. So it's a measurement, it's a test method. It's not a specification, it's a test method. So it won't tell you, it does not set the limit of permissible value. It does not do that. It's a standard method. And what the output will be is just a table of numerical value. And from there, you can decide what you want to do. And then it will cover, it does not cover yet, lamination and installation. Once we master the monolithic, then we can think about doing more complex things. One of the interesting things of our last meeting, so this is meeting number 7, we determined what would be the acceptable value for machines. So we as a strict range, we say that the machine has to go from 0 to 120 nanometer retardation. We're looking at the technology, I think we can reach plus or minus 10 nanometer precision. So that's the idea. And we want to have a bias, that's the language for ASTM, but it's a repeatability of 5%. So if you take the same glass and you feed it through 2 times, 3 times, 5 times, your value will not vary more than 5%. So that would be the basis for our test method. That's what we want to achieve. We know that there are machines with different capabilities. Some have more limited range, some have more. But at least that's the basic. The very start is that if you want to measure anisotropy correctly for monolithic heat-treated glass, you need that range. Below that, you won't be able to, or it will not be significant. Now, just what's next for me, or for anybody who wants to take my thing, is basically officialize that base block. So we'll submit our draft document for ballot. I hope to do that as soon as possible, maybe this summer. Then what we want to do is to watch what's happening beside that, because there's much more than than measuring it. You have your map, you have your data, but how do you evaluate that data? How to describe the light environment of the building, because that's important also in your results. How to create realistic glass rendering for architects, so how people will be able to see that. And how is our eyes reacting to all this? So our eyes as a function which is called the contrast sensitivity. So if you look at this thing, you have region where you don't see. There are differences here, but you don't see them because the spatial frequency is too wide. There's region here that you don't see, the differences in the bar. That's how your eyes functions. But this is well understood in the display industry, but in the glass industry, nobody speaks about that. But that what influence what you see when you look at the building. So that's the important part. The contrast sensitivity. And that was discussed in Cupertino when a presentation from McMaster University, Mr. Kitai, developed that. So we need, in the next step, we'll need to know more about how our eyes works and how we can work with mathematical average, island of high retardation in a thing, in how to treat the edge, what region to exclude in our measurements and all this, and what to do when we have glass that are with different geometry, because that affects a lot the level of anisotropy. And define a mathematical method that could help us to work with large retardation data. The other thing we can see is that if we are able to measure the light environment of existing building, so you're going to build this thing just beside the Thames in London, by the water, what will be your polarization level? How the light will be polarized. And already there are companies, there's a French company that work on that, and that can give you rendering with different light environments. So the same facade with different illumination, they will render you what it will look in different polarization. But if you want that to be accurate, you have to know what is the environment of your building, because it will change. So, key takeaways. Now we have enough computer power, and it takes pretty hefty computer to compute all this in direct time. But you see I presented 5 different scanners. Company that makes scanners, so you can buy a machine tomorrow that will be able to read either online on your tempering furnace or offline. We can definitely say that optical retardation mapping at 0 degree will definitely give you a good idea of how good is the tempering process. That's for sure. And once we have an ASTM standard, you will be able to say between 2 parties, between an architect and a fabricator, people will be able to say, I like this glass, I don't like this, I want this level, I have this number, and people will be able to commit to that number. So that's the purpose of that ASTM standard. I thank you.
Thank you very much, Louis. Now we have time for questions. Over there we have one question.
Oh, from our most important stakeholder.
Good morning, Luis. 3 questions that are similar.
Okay.
I mean, I have more questions, but I think I'm going to let them ask them. The first one, what is the timing for the first ASTM publishing of the work that you've been doing? Before you answer, what is the timing for the next steps that you have there? And before you answer, what is the timing for the next time we meet in Cupertino?
I like the pressure. I like the pressure.
Well, if you want to keep the pressure, we can set a date for the next Cupertino summit. That would be my pleasure. Hoping to go into the round headquarters this time. But yeah, so right now, I would say 90% of the standard is written. I have it. I have a few copies with me. If you are interested, I can give it to you, paper-wise, or can send you a PDF if you want. I'm not too familiar with the ASTM method. I know we have to go to ballot, but I don't know too much what it involves and how much time do we have, and how much objection. I think the main concern with ASTM is that you have to answer any question that arise from your balloting. So I cannot predict how many questions we will have. We'll try to answer them as fast as possible. Up to now, we've been pretty streamlined. We don't have a big group. We're working with about 12 people, and there's a lot of enthusiasm in the group to come up with something rapidly. But I would like personally to go to ballot this summer or early fall, and then from there on, I don't know when it's going to be in standard. But you could still, once it's for ballot, you can still reference to it. As a fabricator or as an architect, I mean, it will be something written, so you can see. I'm against that piece. That something is written. You have in an ASTM format with all the paragraphs that are pertaining to anisotropy, to the measurement method. Does that answer your question? And if you want to set a date, yes, we can say. I mean, the sooner we meet in Cupertino, the best. I mean, I think we should wait for the ASTM outcome, and then I hope that this thing, because when we first started the task group, we were quite specific on the participant, but on the next task, I think there will be follow up by another task group that will be more working on a specification, or at least a mathematical analysis of the data, and that will be the next building block in my book. But I mean, everybody is welcome to participate in that next stop, in terms of getting things starting from the building block, but then coming up with something that will be more useful with a specification.
Very good. Just a short comment on that and the how you can reference on certain standards or certain papers. Now, even after that meeting, and I'm now talking from a tempering line manufacturer voice, even after that meeting, we have started to see class professors making reference to things discussed there. So that's interesting how things go forward. So you can start to implement certain things already before there is a standard. But now that we have a question from Saverio.
Yeah, I remember that guy in 2013 talking about anisotropy.
he's the one who presented his 13 or 15.
Nobody wanted to talk about it. And now you've got multiple presentations, people outside. So well done, really, that's fantastic. And one of the things I said was it was a great opportunity for the glass industry to exploit. And I'm glad to see that everybody really bought into that, including Glaston and all the other players. One of the key things that we said in Cupertino was that we needed to ensure that any American standard was coordinated with any European standard. Is that happening? Because the last thing we want to is to have someone measuring in nanometers, someone measuring in inches, someone measuring in Pascal or whatever other things. Where are we with that, Louis?
We started to work a little bit with the DIN, but I discovered that there is really a lot of political things between the different agencies. ASTM is a business, and they don't want their wording to be repeated as is in other standards. Same thing, so there's copyright issue and everything, and it's not a simple matter. But I would like, and we use research coming from Europe, and I would definitely like that to be replicated on the ISO level. But right now I'm concentrating on ASTM, but it's good for you to remind me that we should be also recontacting ISO and then to make sure that we could work together on that. So we have something that apply also for Europe.
Saverio just on this, and in CEN, so the European Standardization Commission, no work has started there. So in Europe, it's in Germany in the FKG, so it's an association of for constructive class. There was a task group, and they have made a first document on anisotropy, and it's very coherent with with the work done in ASTM. So it's the same language, same measurement method. It's really it's almost the same.
And if you want to contact me, I can give you a copy of that document also. It's a very well done document. It's even better than what I presented here. But I hope you enjoyed my presentation, and that we will work all together to better that phenomenon and understand more also what applies in more complex assembly, because that's one thing that happens. I talked about anisotropy in plastic, same phenomenon, different visual out of it, but also very important for the aesthetic of our buildings.
Very good. That will definitely be the next step, talking about different kind of complex assemblies. So once again, thank you for Louis Moreau.